This is Decrypt's Encryption Basics 2 video. Please check our website. The last video ended showing the cryptanalyst defeating Shift or Caesar because he only had to try 25 keys. Shuffle has enough keys that even if your cryptanalyst can try 1 billion keys per second, an asteroid will likely hit the Earth before he finds your key. All of Shift's substitution alphabets are so well ordered that once the cryptanalyst knows any plain text encrypted text pair, he knows the entire alphabet. Shuffle randomly rearranges a substitution alphabet like shuffling a deck of cards. Shift only has 25 possible encryption keys. If you count the zero shift, it has 26. Shuffle includes all of Shift's keys and a whole bunch more. Let's see how many. Now, you don't have to know this math to use encryption, but hopefully some of you may be interested in math, so we'll show you how to figure out how many substitution alphabets you get from using the shuffle method. If your eyes glaze over on this, just skip the slide. So we'll start with A. You got to choose a letter that you're going to substitute for A. You have 26 choices. Let's choose H. Move on to B. Oh, you can't choose H anymore. It's only 25 choices. Let's choose X. Move on to C. Same deal, so let's choose M. When you finally get down to X, you only have 3 choices left. Same for Y, you only have 2 and 1 for Z. So we multiply all these out, we get 26 times 25 times 24. That equals what mathematicians call 26 factorial. That's that 26 with the exclamation point at the end. How big is this? It's huge. Shuffle can make so many substitution alphabets that we're going to assume the cryptanalyst can try 1 billion per second. How long is it going to take him to find the particular shuffle substitution alphabet you use? Let's see. Well, if 1 billion takes 1 second, 10 billion takes 10 seconds. 60 billion takes a minute. 3,600 billion takes an hour. 90,000 billion will take a day. 32 million billion will take a year. 32 billion will take 1,000 years and will still not close. This is so many possible keys to try a brute force attack that a quite viable strategy is, let's wait for a couple of years for computers to get better. So now you know your key is safe from the cryptanalyst's exhaustive search or brute force attack. Here's how you use our shuffle. Here's a picture of our shuffle cipher, and notice that the shift button has been replaced by a shuffle button. Each time the shuffle button is hit, a new random substitution alphabet is created. So now we know how to create a shuffle substitution alphabet. We'll replace that simple shift substitution alphabet, and encryption works the same way. Some of you may have noticed that N is getting encrypted to N and reasonably ask, hey, that's not an encryption. But it is. Cryptographers don't want to give the cryptanalyst any unnecessary clues, and if we don't let any clear text letter be encrypted to itself, then the cryptanalyst only has to try 25 letters, not 26. And in fact, this kind of hole helped the Allies break the German code during the Second World War. Let's take a look at what a shuffle substitution alphabet's key looks like. For this particular shuffle substitution alphabet, 13, 13, 5, 2, etc. A plus 13 is N, B plus 13 is O, etc. move Shuffle's key up here and we'll compare them to Caesar's cipher. Both keys are 26 long, one for each letter of the alphabet. This is one of 26 Caesar shift keys. This is one of a lot of keys. And since we're talking about the number of keys a method has, let's compare Shuffle to AES 128. Shuffle has this many keys. AES 128 really has 2 to the 128th power keys. How many more keys is that? It's a trillion times bigger than the number of Shuffle keys. This is all pattern, and if made correctly, this is no discernible pattern at all. Shift key is easy to remember, it's only one number. Shuffle key is very hard to remember. So here's what we mean by moving target. The cryptanalyst goes, "Hey, I'm going to find your key pretty quick." Cryptographer goes, "That may be, but you're not going to find this key so fast." But the cryptanalyst isn't done yet. He's going to attack the encrypted text directly with these letter frequencies. And there are plenty of them. The take from this is that having a lot of keys is only half of a secure method. Let's see what I mean. So take a look at this made up clear text and encryption message. You might notice that there are 4 F's, and P and W also gets repeated. Letter frequencies can be used for cryptanalysis the same way as a brute force attack. The cryptanalyst is going to replace the F's by E's, the P's by an N, and the W's by a T, and the encrypted message is nearly revealed. So if you kind of like these puzzles, take a look at our puzzles PDF, and you also got the whole solution if it gets too frustrating. So you might reasonably assume that your cryptanalyst is not going to do that kind of work to break your Shuffle key. But since those Shuffle keys are really too hard to remember, let's introduce a simple password. Here's a Shuffle substitution alphabet. Store that down here for comparison purposes. Get a password as shown here, and here's what a Shuffle substitution alphabet made with a password looks like. Get the audio-visual team to pump it up a bit, take a better look. Default P becomes the first few letters in the substitution alphabet. Well, what about the A? Well, remember, Shuffle is shuffling the alphabet like a deck of cards, and the A has already been used. Likewise, we'll use the first S, W, O, and R, not the D. That uses up all the letters in our password, and we'll complete the substitution alphabet with the letters of the clear text alphabet that haven't been used. One last thing before we leave this slide. Again, depending on who your cryptanalyst attacker is, you don't want to give him too many clues. Take a look at the end of our default password Shuffle compared to a normal Shuffle. See the clue?
Didn't he just say that there were as many possible shuffle alphabets as stars in the universe? So what is it with only one alphabet?
She's right. Every time you hit the Shuffle button, you get a new shuffled alphabet. And even though there are more substitution alphabets than there are stars in the universe, once you decide on a particular shuffle, the other Shuffle substitution alphabets don't matter. You're only going to encrypt with this one. And since there's only one substitution alphabet used for encryption, if he figures out that H is really plain text E, he knows that every H is clear text E. So he's got one less letter to search. And this, of course, happens with every letter he finds. The next cipher we'll look at fixes this weakness. Secure methods definitely need a huge key size, but they also must stop frequency analysis. The next video shows a method that will encrypt E's differently for each letter. It has the added advantage that it can be used as one of the provably secure ciphers.